So now we're going to look at a graphical approach of how to find like how long it takes for a population to hit a certain number or for something that's decaying to hit a certain value. The standard exponential population model that we'll be using today is P naught times 1 plus r in parentheses raised to the t power. And then I have each of the variables here defined for you guys. So P naught, as in NOT or P sub 0, either way, this is the initial population. So if they say that you have a certain amount of something in the beginning, that's the number that you're going to plug into this spot. Next, you have the R value. This is the trickiest one because if it's a rate of growth, then it's going to be adding on to 1. If it's a decay, then you're actually going to be subtracting from 1 because it's a negative number for R. The other thing that's important to note is I specify that this is decimal form. So you have to make sure that if they give you something like 5% growth, you need to remember that you take that 5% and you move the decimal space over twice to think of it as 0.05. So 5% growth would actually end up being 1 plus 0.05 in here in the parentheses. If they said it was a 10% decay, you move the decimal place over twice, and since it's decay going down, that would be 1 minus 0.1. So you would end up with 0.9 inside of the parentheses here. And then t is going to be the time in years. Usually that's going to be the value that you're solving for. And for graphing purposes, you can plug in x for that on the graph. And then the x value we find will be how many years it takes for us to hit the target number. So here's the process we will use for solving exponential growth and decay models. First, you're going to have to set up the model for the exponential function. And that will be based on the information they give you in the problem. They should tell you what the initial population is, and they should define some kind of a rate of growth or decay. Just make sure you remember to change that R value into decimal form before you either add or subtract it from the 1 inside the parentheses. Then you're going to use a graphing tool. I would recommend Desmo's graphing calculator because that way you can put, I know you can put multiple functions on there and then find where they intersect. If you have some other kind of graphing calculator, that's fine. But you're going to plug in 2 different equations. The first equation is going to be the model that you made in step 1. So the model is based on what you have from the previous slide, that equation that you created. The second equation you're going to plug in is going to be the target number they give you. Like maybe they'll say, at what year will the population be 1 million? Then you would just plug in y equals 1 million for the second equation. If they say they want to know how long it takes till you hit 50,000, you would plug in y equals 50,000. And so you should end up with 2 different equations plugged in, and then you might have to zoom around a little bit, but find where those 2 graphs cross each other. If you click on Desmo's graphing calculator, it'll even give you the exact x value, and usually we'll be rounding that to the nearest value, but that'll depend on one question to the next. So the beginning of the assignment will be pretty straightforward. You won't even need to use the graphing tools on this yet. They're actually just going to ask you, according to the definitions we've looked at, is it an exponential growth or decay function? To determine that, you need to look at what is being raised to the power. If this number is bigger than 1, then that means they must have added a positive number to 1, which means that we have an exponential growth. If this number being raised to the power is less than 1, so you end up with something like 0.93, 0.8, whatever, then it must be exponential decay because they started from the value of 1 and they subtracted a percentage from it. So the R value was negative, indicating a decay. So on this first example here, they ask us, is it exponential growth or decay? And then, like I said, since I can see that this number is bigger than 1, that means it is growing. If you multiply by something bigger than 1, it's going to get bigger. So this function will get bigger from one x value to the next. And then next, they're going to ask you what exactly was that growth or decay. Well, in decimal form, we're looking for the difference between the number we have here and 1. So we have 1.04 minus 1, which gives me 0.04. Now that's the decimal form of the value, but to change this into the percentage, because they're not asking me for the decimal form, they want the percentage value, I need to move the decimal 2 spaces in the opposite direction from what I was talking about before, because I want to change it back to a percent. So this would end up being 4% growth. Jumping ahead a little bit, now we're being asked to determine what the model is, or the exponential function they may call it, based on them giving us a couple of pieces of information here. So again, if you look at our notes, what we had for the rule is the initial population times 1 plus r, and r could be a positive or negative number depending on if it's growth or decay, so look for those keywords, raised to the t power. So for our example here, we have an initial population of 415,000, and then we're going to be multiplying that by 1 plus r. Now, in this case, they say that it's increasing, but I need to make sure that I get this number into the decimal form. So 3.8%, if you move the decimal space over twice, then you're going to end up with 0.038. So that's the decimal version of 3.8% growth. And then inside of the parentheses, we need to be taking that r value and adding that to 1. So in this case, I'm going to have 1.038. So 1.038 is the 1 and the r combined, and that's the number that would be getting raised to a power. And then the exponent we'll be using for these is going to be based on t for time going by. So the most important thing is just be careful about remembering to change the percent into a decimal, and be careful about whether they say something about growth or increasing, then that means add the number to 1. If they use the terms decreasing or decay, then you need to take that decimal and subtract it from 1 because your r value is negative. And here's jumping ahead again, how do we actually find what year a certain population will be hit? So they've given us an initial value. We know that P naught is going to equal 673,000. And they said that it is increasing at a rate of 1.46. Now that's 1.46%. So I need to move the decimal space over twice again, which means the value I'm going to have being raised to a power will be 1.0146. And that's because this is, again, increasing at a certain rate. So add the 0.0146 to the number 1. So we have our initial value, we have our r value, which means that the formula we're going to be using for reference is 673,000 times 1.0146 to the t power. So this is our model. Now we're going to have to graph from what we've just determined here. So looking back at what we had in the notes, let me clear out what I just wrote in there. We said that we need to set up the model, which is what we've just done. Now we have the model 673,000 times 1.0146 to the t power. Now we're going to switch over to using Desmos graphing calculator, and we're going to plug that in, and we're going to find what is the target value that they want us to hit at some point, and then we'll be able to solve for t using this. So here's Desmos graphing calculator. Now I'm going to type in the y equals 673,000 times 1.0146, and then we're going to raise that to the x power in this case because our x and y plot is based on x numbers instead of t values. Now the second thing we need to determine is, looking back at the question, we need to find the target value. And they say they want to know how long will it take for the population to be 1 million. So 1 million is going to be the other value that I'm plugging into Desmos graphing calculator. Now that we have both of those plugged in, I'm going to go ahead and erase the formula to get that out of the way. We just need to find on a graph where these two things intersect. Now, like I said, you might have to play around with zooming because since the numbers are at 1 million and you're probably zoomed in way down at the bottom, just zoom out a whole bunch and then find where your, in this case, green and orange lines are intersecting. And once you can identify that place pretty well on Desmos graphing calculator, if you click on it, you'll see that it actually brings up a precise point for intersection between them. So the value is that 27.321. Now that's the exact value, but I think if we look at the directions, it's probably going to tell us to just round to the nearest year. So we're probably just going to be plugging in 27 for our answer as to when these two functions meet. So sure enough, the directions say type a whole number. So at what point in what year will the population be 1 million? Well, our number from the graph was 27. But if you remember the way our function is determined, that's based on how many years past the initial value, which was from the year 2000. So we're not typing in the year 27. That would be weird. That'd be a long time ago. We're actually trying to type in the year 2027 because the idea is that we just found 27 more years from this start date is when the desired outcome occurs. So I want to show you guys one more quick example because sometimes you won't even have to find the model yourself. They're going to give you a very ugly looking equation that has already been determined to model the population or whatever the value is. So in this case, you can see that we have 1001 divided by 1 plus 90e to the negative 0.2t power. Just as a quick reminder, the value e is a number like pi. It goes on forever and ever and ever. It comes up with a lot of exponential functions. It's approximately equal to 2.7182818, and it goes on forever. But if you just type e into Desmos graphing calculator, it will know exactly what you mean. So in this case, we have our function that models the population growth, and then we have a target number. They want to know how long will it take till we have 600 centaurs. So we're just going to type in y equals this ugly mess and y equals 600. And I've already gone ahead and done that in Desmos graphing calculator just to save a little bit of time on this. So I'll show you, and then we can determine how many years it takes for the target value. So like I said, I already typed in the functions here, y equals 600 for the target value, and y equals the 1001 over 1 plus 90e. Be very careful about your use of parentheses, making sure that you divide by this whole expression. That's why I put parentheses around the whole thing. And I wanted to make sure that it had both the negative 0.2 and the x in the exponent. So I put parentheses around that as well. So once you get those two functions typed into your Desmos graphing calculator, you can zoom around again until you find where they intersect. And in this case, by clicking on the dot, I see that it's at exactly 24.5. So your answer on that last question, depending on how they ask you to round it, if they say to the nearest tenth, for example, you would say 24.5 years from the starting value, or 24.5 years from now, if that's what they're asking. Or they may ask you to go to the nearest whole number, which in this case would just be 25 years. So that's all for the notes. I hope that'll be helpful on the assignment. Thanks, guys.